All right, so let's get started for the day. And I mentioned, I think yesterday that I updated the slides. So yeah, okay. So I'm gonna just like read you a little bit of this part, because last time the majority of the material was updating the beta prior, and then I accidentally only like recorded one portion, so that's why it was a longer than usual lecture video posted. So today we're just going to start from this part again, but I added some new material, so there's a little more stuff to talk about. And then once we're done with this part, we're going to do a lab, and I hope everybody brought laptop. I already posted the instructions online, but we're going to go through that together. Okay, so to wrap up this particular section on Bayesian inference with continuous priors, we're going to do hypothesis testing, credible interval predictions. Okay, so those are the main things we're going to cover. And this, last time I talked about it, suppose one of the Tokyo Express workers claims that at least 75% of the customers prefer Friday. How to test whether this is a reasonable claim or not. We're going to return the posterior probability of this unknown parameter p at least 75%. So what I shared last time was a beta underscore area function that you can use, which is in the TeachBase package. That if you do it, it actually automatically generates a graph for you, so you know it is the area shaded in yellow that is that we're computing. And then, as you can see, you put in so this stands for low, this stands for high, so you're getting that interval. Okay, and then you input the shape parameter. These are the two posterior parameters that we have for the posterior of beta, so that's what you have. And once you do it, you see that, okay, the probability is about 4%, and then it is low, so we are able to reject the claim. And then this is an exercise for you to do it later. And last time I mentioned that you can also do it without the use of the TeachBase package, because in R, there are various functions about beta. We can use R beta, D beta, P beta, and Q beta that you can use. We're going to talk about which one you can use for this case. Thank you. For this case. And also you can confirm that even if you don't use the TeachBase package, you will get something pretty close to this. Right? So, and by the way, the reason why we can do it because we know the posterior distribution to be a beta. We know the parameters for those. Okay. So, in addition to the beta underscore area from the TeachBase package, we can also use the p beta function. So that's the one that you'll be able to use. As you can see, it's sort of slightly simpler. You input like this one. It's like the high earlier. Okay, and then this this number is the low. Okay, so what we're doing with this function at the moment is we're gonna get the p beta function evaluate at 1 minus the p beta function evaluate at 75%. Okay, and then we get the difference. Then we're gonna get exactly the probability for that particular interval. Okay, and we get this as a very close to 0.04. It's 0.09, 0397, blah, blah, blah. So this, as you can see, gets us very close results. And I put this too as exact solution because, as you can see, we're utilizing the fact that we know it is a beta distribution. Okay, and then we're not doing any kind of simulation. But what I'm going to introduce next is, yes, since we also know it is a known beta distribution, we can actually generate a large number of samples from that beta distribution and then summarize. Okay, so that's what you probably know about the term Monte Carlo approximation, which we, in the textbook, is a separate chapter, but I'm trying to introduce those ideas throughout the inference that we're doing. So for this case, you probably guessed what you can do is you can generate a large number. Here, I'm generating 1,000 samples from the same beta distribution. And the same data distribution, obviously, is the posterior. And you input, so S, I define it outside, so later I can easily change it. And then I insert that into how many copies I want to generate. So, and I name this vector called beta samples, okay? And then once I have this, I'm able to summarize. And pretty much what I'm summarizing is, so you all know this is a logical operator, right? So I'm counting how many observations or how many samples out of the beta samples vector that is at least 75%. And then I take the sum, because that's logical, that's true or false. And then I take the sum and divide it by the total number of samples I have, which is going to give me an approximation to the exact solution. And the approximation, as you can see, is pretty close. It's 0.0737. And you can actually increase this 1,000, this number. If you increase it even higher, I think you're going to get an even closer approximation to 0.04. Okay, so this, I think some of you already covered this. In other courses, you're learning from other sources. So this will be an approximation through Monte Carlo simulation as an approximation to the exact solution. So as you can see, if you know exactly what the posterior distribution is, you're able to either use the exact solution or to use approximation through MC simulation to conduct a hypothesis testing. Okay, the goal is to summarize the posterior, whichever you prefer. That's up to you. Okay. All right, so that's some addition from what we did last time, and that's just for Bayesian hypothesis. And last time I also talked a little bit about the Bayesian credible intervals. I think that's roughly where we stopped. So again, Bayesian credible intervals, we know it's a direct probability statement about the unknown parameter. We're trying to come up with an interval that has certain probability to contain the unknown parameter. Okay. Again, in contrast to the frequentist credible confidence interval, this Bayesian credible intervals are direct probability statement about the unknown p. So a Bayesian 90% credible interval, it will be an interval contains 90% of the posterior probability. And the demo that I did and I'm doing now is using the teach-based package, which is the beta underscore interval. So here you see that I'm trying to return the middle 90%. Okay, so I put 09 as the first input, and then the second input is the vector of the two posterior, the parameter, the two shaped parameters in the posterior of the beta. And you can see this function also automatically plots you a graph, and then you can see that it's the shaded area in yellow that is the credible interval that we're trying to return. Okay, so of course you can you notice that if you're going to use this function, it's only going to return you the middle 90%. Sometimes you might want to have, say, so middle 90% means you have 10% left out, right? So it's 5% on the left, 5% on the right. Sometimes people might want to shift it around. So this function, unfortunately, only allows you to do the middle 90, but that's typically what people do anyway, so you can go with this. But if you want to do, say, let's see, if I want to do a middle 90, if I want to do a 90% credible interval that is not in the middle, I want to have, like, say, 2.5% on the left and then 7.5% on the right, then this function doesn't do it for you, but you can easily do it using the embedded R function that it's in for beta. So first of all, this is still exact solution. I told you only the middle 90% you're able to use the beta interval function. And if you want to not necessarily get in the middle 90%, you can use the Q beta function in R. Okay, so the demo here I'm doing is still the middle 90%, just to as a comparison to the beta underscore interval. But you can see that if you want to get the middle 90% from the Q beta, you pretty much were leaving 5% on the left and 5% on the right, right? And then you can return this to, pretty similar to what you get from the beta underscore interval function. So this, I put it in red, that's not necessarily the middle 90% because I can easily, say, change if I want not a middle 90%, but like I said earlier, I want 2.5% on the left, and then that means I need let's see. No, this is wrong, right? I need to shift further. Sorry about this. Okay, should be 2. Right? Because I'm trying to get the 90%, so I need 2.5% on the right, and then 7.5% on the right. Oh, 2.5% on the left, so it's 7.5% on the right, right? So then in order to get this, I can return these two numbers, okay? So this is gives you the flexibility to not only just getting the middle 90%, but like if you want to shift it a little bit more to the left or right, you have the flexibility if you use the Q beta function. Okay, so this again gives you what you want, and alternatively, you can do it through Monte Carlo approximation. So again, what you can do is very similar. You just set seed and then determine how many samples you want. This is exactly what we saw before, okay? But in order to return the confidence, the credible intervals, we use the function called quantile. So that's R function that directly, so you have 1,000 samples here, and the quantile function will just return you the quantile, I mean the numbers that the two quantiles that you specify. Okay, so this is an example again of the middle 90%. Okay, and then this will be the numbers. So again, either through exact solution or approximation should get you very similar results. So say if a question asks you to return a credible interval or to do a hypothesis testing, you can do which way you prefer. Okay, there's no fixed, and I'm introducing both to give you an idea that you can really do either one, and then if you have time to do both, you can actually confirm that both of the answers are correct. Okay. All right, any questions? Okay, all right, if not, I want to talk to you about the new topic here, which is the Bayesian prediction. So the prediction itself, I mean, is a key component of doing statistical analysis. A lot of times people want to know what would happen later, right? So in here, suppose the Tokyo Express owner gives out another survey. I'm using a different number now, notation. M k equals to M, but let's do it more generically. Let's do a different number of like survey respondents, in this case M. And suppose now the owner gives out another survey to M customers, and we'd like to know how many would prefer Friday. Okay? So this, as you can see, mathematically, we're trying to get to this predictive distribution. So notice the way that we're writing it. We use y tilde to be any kind of predicted value in the future, okay? And then what we're doing now, as you can see, this is a conditional, meaning that we're looking at the distribution of the predicted value given what we have at the moment, okay? So right now, we don't see any kind of parameters. That's only because essentially we try to like integrate out of the parameter all over. Because whenever you have a parameter in the model, you're making assumption about the model, right? And the parameter is just something that you describe, you're using to describe your model, and then essentially the predictive distribution is sort of independent of the parameter. You're really just asking about what will be a future predicted value if I know that in my current sample I have y out of n to be preferring Friday. So this is what this conditional distribution here means. But of course, if you just look at this, we don't really know what to do to go to next. So you will see that in order to compute this predictive distribution or calculate this or express it, we're going to introduce the unknown parameter into it. And then you're going to see how, in the end, we're actually using what we know about the posterior distribution of the unknown parameter to help us to make prediction of a new observation. Okay, so let's see how we can do it. So people work on exact prediction. You can actually prove it. It's not the focus of our class, so I don't want to get into it. But if you're curious, the exact predictive distribution, if you're using the beta binomial setup that we're doing, is actually a distribution called beta binomial. Okay, and then it has these 3 parameters in here. Not to worry about it. I think it's just too much being involved as how to sample it directly from here. But our focus will be, well, in this case, we know the exact predictive distribution. It's hard to sample from it. but still we have it. But a lot of times we don't have the exact predictive distribution, okay? So the general approach is that instead of finding the actual exact predictive distribution, we're gonna sample, in this case, 2 steps, okay? Because ultimately we want what? We want y tilde, right? And y tilde, if we assume the same binomial like setup for a y tilde, it will be this distribution, right? Except now, this is not a prior anymore. This is the posterior that we have, right? So whenever we're making prediction based on whatever we have already, this is the general data model. But this data model right now, conditioned on the unknown parameter, we want to include all of the information that we have previously, right? And the way that we're doing it is to generate new y tilde from the posterior distribution of theta, okay? Because now we know better, okay? So it's from what we know before. So this is still the general setup, okay? So as you can see the setup over here, we can generate a y tilde from a binomial distribution if we know the value of theta, right? Because that's just what the data model is, right? So that, as you can imagine, will be the final step when we generate a new tilde. And in order to get a new value of theta, as you can see, we already know the posterior distribution of it. It's a beta distribution, right? So intuitively, you can, first of all, generate a sample from the posterior distribution of theta, and then given that value, you generate a new y tilde. Okay? So that's the step that, because we already know the posterior distribution of theta, we know it, right? It's what? Theta a plus y and b plus m minus y, right? So essentially step 1, you are generating a new theta from here. And then step 2, this is the posterior, it's worth highlighting. And step 2, it's going to be a binomial because now we're given the sample to n survey respondents. So total trial is n, and then whatever the theta value that you had previously. Okay? So this is a 2-step process, but it's, I mean, first of all, it's more intuitive, I think. Second of all, you already know the 2 distribution. One is beta. I know I can draw from R beta, right? And then another is binomial. I know I can draw it from R binorm, right? So the key is how to make the link and how to, first of all, get the draw for theta from the posterior, and then from there, how to get the predictor. Okay? But the general procedure is like this. Cool. And I should also say earlier here, I presented the exact solution. So if you know, if you search online how to sample from this beta binomial, you can find resources and you will be able to generate y tilde directly. But a more intuitive approach and more, I guess, accessible approach in the future as well is to generate from a 2-step process. Okay? And you generate a draw from the posterior of theta, and then given the theta, you generate a new predictive value from the data model. Okay? And that coincides with what we saw before when we actually do the Bayesian inference, right? Theta is from beta, and then y given theta is a binomial. All right, so the way to do it is you sample P. Oh, sorry, I should use P. My apology. Yeah, P is better because we keep talking about percentage here. So P, you sample a P from its posterior, and then you sample y tilde from the binomial. Okay? So our focus for this course is how to do it, do simulation, do prediction through simulation. So this is the procedure, and I present some code. This is also on Moodle if you want to check them out. As you can see, first of all, I set up those numbers, and then notice that I'm just doing a demonstration that m equals to n. Okay? But you can do otherwise. That's up to you. And so what I do over here is, as you can see, I first of all sample S, which is 1,000. I sample 1,000 different values of beta for the value of P. Okay? So from this line, I get 1,000 different values of P from its posterior distribution. Okay? And second of all, is for each of this, so that's the beauty of doing this vector manipulation in R, that if I initially have a vector of length S for P, and then if I just directly input them into the R binorm and specify the right dimension, I will get the same dimension for y tilde, okay? So you can write a loop, obviously, but it's just going to take a little bit longer time. But you can do it in a vector form. So the first line is getting 1,000 different draws from the posterior distribution for P. And then the second line here is for each of the different values that I have for P, and I'm going to do one draw as the y tilde. Okay? And then I summarize. So at the end of the day, I save all of the y tildes, 1,000 of them, into the vector called prid underscore y underscore scene, and then I will be able to summarize them. Okay? So that's what I do if you want to use RStudio to make Bayesian prediction. All right, so earlier I was saying summarizing. What you can do is, okay, what if I want to know the posterior predictive probability of a newly generated y to fall into this interval? Like, what will be a newly predicted y to be between 5 and 15? So that's out of like 5 out of 20, and between 5 out of 20 and 15 out of 20. I want to know that probability. Okay, and then what I do is we can easily. So this is in R. You can just do the summary based on counting how many predicted y values are in the interval, and then divide it by the total, and you get a probability. So that will be something you can do if you're making that kind of inference or probability statement. Okay? All right, that's good. So I think that's the second last topic for doing this Bayesian inference. And oh, I should also show you this really quick. So on the top is just the exact. I didn't show you how to do it. You don't have to worry about it. But I do want to show you that on the top is the exact predictive distribution. The bottom is the simulated, the one that we just did in class that I showed you earlier. So you can see it's roughly a good approximation, but not like perfect. Okay. And of course, one way you can do it is by increasing the number of samples that you draw. So for this demo, it's 1,000. And you can do more. And overall, the more samples that you do, the better the approximation of the simulated results to the exact solution. Okay. All right. Okay. So last thing that I want to talk about before we go to the lab part is this is also pretty important. We call it predictive checking. And the reason, or I should say, like the meaning of doing this is, imagine now we are able to make predictive values of this y. We have y tilde, right? So earlier we did it. We have 1,000 draws of them. And with access to this predictive distribution, especially if you're able to simulate values from it, one good thing about this is you might be able to use this to check how your model is or how good your model is. So for example, now we have done, like, we start with our prior, we combine with the data, we come to the posterior, and then we're sort of like summarizing, but we never know how good the entire inference process is good or not, right? So the way to do it, imagine, now I can generate a lot of simulated values, predictive values from the posterior predictive that we have, right? And if we plot them together, and if we check, say like the observed data, which is y, I think is 12 out of 20, we can see if y equals to 12 actually is very similar to what you can get from the generated, simulated predictive value. If the observed data is very similar to what you can generate, that actually provides like some evidence or some comforting evidence that your model is not doing badly, right? Meaning that, well, I have this model, I have this posterior, and now I'm generating new data out of it, and my old data doesn't look that different. Meaning that this procedure is sort of like fitting our data well. Okay? But on the contrary, if you see your observed data is so extremely different from what you can generate from your model, then that might indicate that your model might not be doing a good job. Okay? So this is what we call predictive checking. And in particular, we focus on posterior predictive checking. So this, again, the prediction is what we saw earlier, is exactly the same form. And what you can do, if you want to do this posterior predictive checking, is you sample a lot of p's from the posterior, and then for each of the p-values, you simulate the same, from the same like sample size of as the original. So you see that I highlight the n over here. So the reason why we keep them the same is pretty straightforward, right? We want to keep them comparable to what we have in the data. So in earlier example, when I talked about Bayesian prediction, I use m. In the demo, I just set m equals to n. Okay, it just happens. You can try other values. But when you're doing posterior predictive checking, because we want to see how well the model is feeding our data, you need to fix your predictive from the same sample size. I mean, otherwise they're never comparable. Okay. So I highlight them over here for you. So keep in mind, because now this is like in the beta binomial case. Later we might get into other cases, and then when you're doing posterior predictive checking, you always need to pay attention to the sample size that you have, because you want to replicate the observed data in some way. Okay. All right. So ultimately, you're gonna get a sample S y tilde over here, and this is approximation to the posterior predictive distribution. Then we can use that for model checking. So give you an idea. Earlier, okay, so this is the R code. You might, let's see, I think, yeah, so here, the only change that I did from before is actually create a loop to write it. You can actually still do the vector manipulation, it's fine. I was just hoping to use the loop to show you step by step. It's really, I'm doing one P and then one y tilde. I'm doing one by one, okay? But you can do it in one line, like 2 lines, you're good enough. And then down here is the ggplot code to plot the plot that I will show you in a minute. So you can go back to use this as a reference. And as you can see, this is, again, S is 1,000, so we have 1,000 new y tilde. I plot them using a histogram, and specifically, I plot the observed data, which is y equals to 12, as a red dot in here. Okay? So, I mean, pretty clearly, the observed data is pretty commonly observed if you are comparing it to the predictive, posterior predictive distribution. So you can use this plot to say that, well, yeah, I think my model is doing reasonably okay. And more formally, what you can do is you can provide either of this or like both of these probabilities. So this is looking at the probability that the observed is larger than any of the predicted, or 1 minus that. So it's either I'm returning the probability like from the red dot. So if we go back here, I'm getting the probability of either this part or this part. Right? If either of this number is small, that means something is not good, right? Imagine if we have a, let me use a different color. I would use a purple. If our observed data is actually something here, then I told you when you compute those two probabilities, one of this is going to be small, right? And this just indicates that what you observe is actually very different from what you can predict from your model. And that is an indicator of a bad model feeding. So more formally, you can return those two. So I did it for you here. But for our case, both of these two are pretty reasonably large number. So I think both of these are okay. So it suggests that the model overall describes the data pretty well. Okay? But occasionally you might see something different, and then that will be an indicator to tell you that you might want to do something else. Okay? But this is a useful tool to do model checking, okay, based on what we know so far. All right, so for me to recap, it's pretty straightforward. We talked about the 3 general steps in Bayesian inference. The prior, okay, that's depends on how you're coming up with it, but you need a prior for the unknown parameter. In this case, the proportion. And then step 2 is the data likelihood part, that you need to know the data model that you're going to use, and of course you have to go out to take the sample or obtain the sample in some way. And the last step is to use Bayes' rule. We talked about in the discrete case, you're going to do a summation. If it's continuous case, we notice that for a beta prior distribution, you can come to the beta posterior, which makes it a conjugate prior. And then once you do that, a lot of the summarization of the posterior is pretty straightforward. And of course, for the beta binomial, likelihood beta distributions are conjugate, so the prior will be beta, sampling density is binomial, and then we know exactly what the posterior distribution is. And then, in terms of making Bayesian inference based on what we know, we talked about the exact solution and the simulation solution. You can try both. And in particular, for the prediction part, I only sort of talked about the simulated approach because it's more natural and also going to help us later. And plus, the exact solution will be too complicated to do, so don't bother. That's fine. But you should know that it's possible you can do it. And then from the simulation approach, if you have large enough samples, you would provide a good approximation. So you can do Bayesian hypothesis testing, credible intervals, Bayesian predictions, and posterior predictive checking. So those are the topics that we talked about. And for today, we focus on the last part. And previously, I mean, especially for the middle part, we spent like the entire lecture last time to talk about the derivation and also like some decomposition of the posterior mean. Remember to see it as a weighted average of the prior mean and the sample mean. And that would be a good way to think about how the prior and the data are contributing to the posterior. We talked about the mean, not so much about the variability, but we did see a plot to show that the spread of the posterior is much narrower than the spread of the prior. Okay, so the spread, because it's a distribution, the spread is conveying the level of uncertainty. So in the prior, you don't have much information. So in general, you're going to have a wider spread in your prior distribution. But once you use the data to sharpen your belief, that variability is going to decrease. And it's usually shown if you plot the prior and posterior together. Okay. So, so that's all I want to talk about for the section of Bayesian inference for proportion. And for the rest of the class, I'm going to pause here for now. And so for the rest of the class, we're going to do a lab. So I think everybody brought a laptop with you. Okay, so go to, and I'll walk around. And if you have any questions with these materials, I'm happy to talk about all this. And what I need to do.
What? Not the specific one.
Oh yeah, go ahead. Yeah. So I will also show. Okay, I think I need to show this.
Oh my lord. Is there anything else to
I can share. Yeah, I think remote student can see my desktop now, right? Right?
What is it?
Yeah, I can see your desktop.
So on this talk that you can see my desktop?
Yes, I can see your desktop.
Okay, awesome. Thank you, Ellie. All right, so let me get on my Moodle.
That's pretty good.
And it's on Moodle for everyone, the instructions, so. Yeah, so it's towards the, no, it's in the section of Bayesian inference for proportion, and it's lab 1, so if you click that, you'll see an instruction. Okay, so this is actually a question from the textbook. I just picked a few parts of the question, not the entire question, thank you. And you can read it through now, and you will see that. So in class, what we've been talking about is using a single beta prior when we're making inference, right? And we saw different ways that, like, we plot different beta priors, and then we said that you can understand, say, like, different beta priors give you different way to express your prior belief, and then you can have certain flexibility when you're doing that. But if you want more flexibility, say I want a special way to express my prior belief, something you can use, especially if you have a binomial data model, is something we call here mixture of beta priors. Okay, so mixture from the name, as you can see, is is a combined of from multiple, okay? And for this lab, what we're gonna do is we're gonna look at a mixture of two beta distributions. One is beta 2.8 and the other one is beta 8.2. So for part A and B, it's not yet talking about the mixture yet, but A and B will be good for you just to get the exercise and then get you familiar with like say summarizing, plotting, using different functions in R for you to do it. So as you can see, this is a binomial experiment. You have N to be 43 and Y to be 15. Okay, so that's the number. And you're curious about the probability of theta. And theta hat, which is 15 over 46. Okay, so A is using a particular prior beta 2.8. Okay, asks you to plot. So this is I'm using the notation in the textbook. Okay, so I'm asking you to plot the prior, the data, and then the posterior as functions of theta. Okay, so find the posterior mode, mean, and standard deviation, and also find a 95% quantile-based credible interval. So you can use the quantile function if you do simulation. Okay. And you do that for B. B is a different prior distribution. Okay, you're using beta 8.2. Okay, so A and B are very similar based on what we saw so far. So it should be straightforward, but take your time to get yourself familiarized with them. And C is the focus, as you can see. Now it's not a single beta. Okay, I'm giving you the PDF. Okay, which sort of looks complicated, but don't worry too much about the detail now. So this is the PDF, and it is given that this PDF is a mixture of the two beta distribution, two beta priors, okay? And it's 75% of the beta 2.8 and a 25% of the beta 8.2. Okay, so that's the PDF, and I'll ask you to plot this prior compared to the two priors that you have in A and B, okay? And once you see that, please describe what sort of prior PM this may represent. Okay? So this is a general introduction. I will stop the recording for a little bit so we don't get too long with white noise. Once people start to feel comfortable like talking about it, I will like start recording again. But the session is still in session. Okay? So let me do this. Stop share. Yeah, so I just want to talk a little bit about part C. And you can do various things, but let's read the question, I guess, carefully one more time. So it's saying, so it does give you the detailed density, which looks a little bit daunting if you want to just like simulate and draw from there. But it does tell you that it's 3-to-1 mixture, like 75% of beta 2.8 and a 25% of beta 8.2. Okay, so you know these two beta distributions were already like by then soonish. Once you finish A and B, you will know how to get those beta prior distribution from beta 2.8 and beta 8.2. And so the way, like a hint to do this, so I'm presenting here in the R console. This is the Bayesian server. And what you can do is, this is a suggestion. One line can get you there directly. So the way to do it that I thought about is I first of all list all of the values of the two priors. So I use A1, B1 to be the set of 2 and 8, and A2, B2 to be the set of 8 and 2. Okay, so this will be, I will use those two numbers later. And what you're going to do, because we already told that this mixture is a 3-to-1 mixture, right? We get 75% the contribution from beta 2.8, and then the remaining 25% from A2. So a pretty simple, straightforward way to do it is I exactly get, let's see, just to be clearer. So I first of all initialize all of the theta values. I'm having 100 over here. Maybe let me do 1,000 so it's smoother. And for the mixture of prior, because I know what? I know it's a 75% from the beta 2.8, right? So since here I'm trying to get the density, I should use the d beta function, right? And what I do, I have, so for d beta, I need to input the theta values, as well as A1 and B1, so which is 2 and 8 in our setting. So you can like input 2 and 8 directly over here, but if you like initialize them outside, you can change them more easily, okay? So this is the first part, which is the 75% contribution from the first beta, right? And the other part is the 0.25% contribution from the other beta. So if you do this, A2, B2. Okay, so this line, I mean, I'm using one line to do the entire task, but this portion of this is trying to get the density contribution, part of it from beta 2.8 and part of it from beta A2, okay? And we put the proportion, which is the weight, here directly when we consider that, okay? So let's try. It doesn't work because I didn't run this, sorry. So if you plot it, you will get something like this, which if you go back to part A and B, you will see that, I mean, beta A2 is the part pretty much on the left, right? And beta 2A is the part that is on the right, right? Because it's not equally divided. It's 3 over like 75% from beta 2.8 and a 25% from beta A2. So you're gonna see like a more, I mean, like a more contribution obviously from the first beta. So you're gonna see more, I mean, more heavily influenced by that part of data, that part of beta, okay? So this is a mixture, and you can see this, I mean, this general shape is different from all of the other beta priors that we have seen, okay? But this does offer flexibility if you want to do it, like say I have a specific belief that I think the prior distribution should look like this or some other forms, then you can do something like this. And also this is a proper distribution. You will integrate to 1. If you imagine, I mean, because what? You have 2 separate proper prior, right? And one takes 75%, the other takes 25%. Each integrates to 1, so they're going to integrate to 1, okay? But more, I mean, more formally, I'm sure you can show it as well. But okay, so this is what I want to get over for the lab. But of course, I know some of you are still working in part A and B. And for the recording purpose, I do want to mention that in order to plot the likelihood function, you can use what I highlighted over here, that you can use the D by norm, and you're evaluating with the number of success, the number of trials, and then the unknown parameters, which is the sequence of numbers that you show. And then by doing that, you will be able to get, let me just show this here, you'll be able to get the likelihood function to plot it, okay? And then for plotting the prior and the posterior together, you can either like do the teach base package that like we saw it before. It can be pretty straightforward. Or you can also do it using either the d beta function or the r beta function. If you generate enough number and then just plot them, it will give you that as well. Okay, so that's up to you. And those I think you'll be able to get from the lecture slides or the R script that I shared. So the new material today for this lab is about this mixture idea. Okay, so mixture idea is really trying to have a weighted like average in some sense. Like you have certain contribution from some beta prior, certain contribution from another, that will be able to help you to come up with the special shape of the beta prior that you have. And if you think about posterior inference, it's not too complicated because you can just separate them all separately, okay? For the first beta, I have all my posterior, I do the analysis just as it is, right? And then for the second beta, I can do it just as it is. And then they are just contributing through the weight to the posterior as well. Okay, so this is a general idea. And that's actually the remaining parts of this question in the textbook. But for the lab, I just want you to focus on the prior part. Okay, if you're curious, you can go to the textbook to that question, which is chapter 3, question 4, to see the remaining parts. I think it's part D and E to talk about the posterior inference if you're using a mixture prior like this. Okay, yeah, so the lab is mostly for you to get familiar with different functions and then make sure that you understand the notation. And I use the notation, I mean, in the question from the textbook, so sometimes it might look different from what we use in class. Say, typically, I use pi theta and pi theta given y to represent the prior and posterior, right? And then this, we rarely talk about it, but if you look at this, this is the likelihood. Okay, this is y given theta. Okay, so that's why. And also, I mean, if you read the question carefully, you should also get posterior mean mode and standard deviation, and also the quantile based credible interval when you submit the lab report later. Okay, but the gist is use either the teach-based package or the basic beta functions, and then for part C, creatively incorporating the mixture weights into the way that you are coming up with this mixture fire, and you can plot it in this way. All right, sounds good. So I think